Welcome to this presentation. My name is Federico Giaimo, and this is continuous experimentation for automotive software on the example of a heavy commercial vehicle in daily operation. First of all, I will introduce continuous experimentation. This is a practice that is used for software development and comes from the software-intensive web-based systems. It is used in a systematic way by many companies on a daily basis to improve their products. Continuous experimentation is based on the classic idea of a scientific experiment. The process can be explained with a simple example. If you're a software engineer at, let's say, Google, and you want to improve the search engine algorithm by using this practice for testing different versions of the software to find which one works best according to your set goals, first of all, you would identify the user base that will take part in your experiment. Then you would divide this user base in partitions or clusters, and to each of them you would deploy or give access to a different version of your software called experiments. The difference could be in the parameters that you use or in the algorithm the software is based on. One of the partitions, however, will still use the previous version of the software, acting as a control group for the whole experimentation process. Each of these experiments is also collecting data that is relevant for the experiment goal. This data will be analyzed to decide which software version performed better. The winning software version is then applied to the whole user base. The result is that the software evolved from the blue version to the green version, not because of guesswork, but because the real-world data showed that this new software version was closer to achieving the experiment goal. In this research work, we looked at automotive systems. These are safety-critical systems that run on distributed software, which performs continuous hardware interactions to sense and manage the status of the vehicle. The software is run in several interconnected computing nodes that are represented by dots here in the picture. In the chart on the right, you can see the amount of software that was present in a number of vehicle models up to a few years ago, with the last model reaching 900 megabytes of software 6 years ago. These figures can only increase considering the fact that automated driving functions and driver assistance systems are becoming more and more common in vehicles, increasing the need for software practices that can help to give a fruitful direction to the software development process. Now we'll go into the technical aspects of this research work. The context of this work was the AutoFreight project, where a commercial truck used daily by its owner company was equipped with computing units, sensors, and remote data connection capabilities. This is the architecture of the system. The computing units were connected to cameras, GPS sensors, and the vehicle CAN network, as well as two 4G routers to guarantee external connectivity. An important aspect in the definition of the system was redundancy. As the system is in daily operation, we researchers have seldom access to it. This means that in case of issues, the troubleshooting work will most likely take place remotely. Redundancy helps also to achieve a graceful degradation of performances should a subset of sensors or computing units malfunction. This is the software architecture. The developers in the HQ box to the right deploy production and experimental software modules to the system. They also interact with the continuous experimentation supervisor in the center of the picture by providing the experiment protocol, which is the set of experiment parameters, and receiving the results report at the end of the experimentation process. All communication to and from the developers is done using an over-the-air remote data connection. The supervisor module is the one in charge of the smooth operation of the experimentation process. It monitors the performances of production and experimental software modules to make sure that the experiment parameters are not violated, and if violations are indeed occurring, it has the power to ask the experimental software module to reduce their resources consumption by issuing a degradation command. Or or if the violations are deemed too severe, it can abort the experiment by issuing a stop command to the experimental modules. The result of this work is the software architecture that demonstrated the adoption of a continuous experimentation decision cycle focused on an algorithmic experiment performed on a computational system housed in a commercial vehicle, where the deployment of the experimental software to the system and the retrieval of gathered data are performed via mobile data connection while the automotive system was operated by the owner company. In a previous work, we identified a number of design properties for the software architecture to enable continuous experimentation on an automotive system. In this paper, we discussed these properties in light of the architecture designed for this research work. Among these properties, we find, for example, access to perception sensors and systems, or the logging operations for internal activity of the system and instrumentation of the software, which means the collection of relevant data for the experiment's goal, but also the creation of a bidirectional communication channel between the developers and the system to deploy new software and experiments and to collect data back. We found that the properties that we proposed do hold, and the only discrepancies are accounted to the difference in scope between the two studies, as the original study focused on automotive systems capable of driving autonomously. To summarize and conclude, in this work we proposed a continuous experimentation decision cycle to test an algorithmic hypothesis. The software deployment and data retrieval operations took place over a mobile data connection, and we performed these operations on a computational system housed in a commercial vehicle operated by the owner company. We propose a software architecture that enables continuous experimentation for an automotive-based system and validated previously proposed design properties in light of this new work. As directions for future research work, we can envision the automation of those steps that required manual intervention, such as the automatic deployment of experiments or the analysis of the resulting data, but also the validation of this proof of concept on an automotive ECU in order to analyze the impact of the limitation of computational resources and how to obtain a continuous experimentation capable commercial vehicle, given the strong software regulations that are in place for automotive software. Lastly, I wish to thank the Reverel Automotive Laboratory at Chalmers University of Technology and the AutoFreight project for the interesting research context that they provided for our studies. With this, I conclude my presentation, and I wish to thank you for your attention.